Hello everyone. Today I will share about our research in EICONCIT, EICONCIT conference. The title of research is Performance of ES920LR LoRa for the Internet of Things Technology Review. Okay, this is an abstract for my research. In this research, LoRa used is ES920LR. LoRa ES920LR is used in Japan with frequency of 920 MHz. And LoRa ES920LR has small dimension. It is the size 24 centimeter and 17 centimeter and 2.3 millimeter for thickness, and a range of 3 kilometer at free space band loss or PSPL, FSPL, and the RSSI value on dBm is found to be different in different outdoor environment conditions. The ES920LR is used as a transmitter and receiver for human heartbeat data. The heart rate sensor used is a pulse sensor placed on the tip of a human finger. The RSSI on the line of sight of building position. The RSSI value is minus 119 dBm at a distance of 710 meters. And the PRR on percent is 93.94%. The ES920LR is combined with the Leafoni board to become the Leafoni board ES920LR. Due to its small size, it is possible to place it a drone or UAV couples with GPS as navigation in the analysis in the ES920LR splitting factor and signal power LoRa. And this is a dimension and radio frequency type of ES920LR E cells. And the dimension is like this. And this is E cell ins from our transmitter. And this is a pin from Leafoni board and ES920LR. We use 4 pin on the Leafoni board and ES920LR. And this is designed from our laboratory. And the voltage is 3.3 volt DC to from Leafoni to ES920LR, and use 2 pin for RX and TX. Use pin 8 and pin 9. And this is approximations from our research is how to apply create the application to drone with the different splitting factor and different bit rate and time on air. And this is how to calculate the time with the 2 parameter, use splitting factor and bandwidth, and how to calculate about the bit rate with the 3 parameter, splitting factor, bandwidth, and coding rate, and how to get the time on air with from the variables and payload. And RSSI LoRa, this is use a dBm equal minus 10 n log d multiply with 10 plus a, and n is environment. So if the uh, communicate will uh, use transmitter and receiver on the line of sight. We use N is 2, and this is an example. A drone communicate to receiver with different splitting factor, and the position of gateway is like this. This is illustrate about position, the splitting factor uh, difference, and this is our prototype, and this is use a pulse sensor. The function is detect about the heartbeat and sending the data or make a transmission data from end device to the receiver, and analyzing process is how to know the packet receive ratio and the RSSI with the different distance. And this is output heartbeat. This is from our heartbeat and sending the data and so on the ThinkSpeak application server IoT real time. And we need to considering upon the power consumption. So on the code, I'm use idle mode. Idle mode is how to make sleep and wake up on the command and wake up while transmitting data LoRa and sleep uh, while the stop transmitting data LoRa. So this is three command, the important command. Number one is how to know the library. So the first time is we use a library like include LoRa and sleep library. So number two is command to sleep. This is sleep while the stop transmit data and wake up while the transmit data. So from this uh, mode on the code, we use sleep and not sleep to make the adaptive data rate on the static condition. And this is a splitting factor analysis from the splitting factor, bandwidth, and time on air. So if the splitting factor increase, like splitting factor 12, and this is make time on air is more high. Time on air on the millisecond is more high, and the bandwidth is uh, very important parameter. If bandwidth high, like for example 500 kilohertz, this is very fast on the time transmitting data from TX on TX and LA. So this is on the 500. This is around 10 or 20 millisecond on the 500. But with the bandwidth small, it's like this is like 55 kilohertz. This is still need the time on air is more high than the 500. 500 like 10, and this is maybe 50 or 100. And the next is about the splitting factor, bandwidth and bitrate. Bitrate is important. We need to know the how much the throughput from the transmitting data on the receiver on the RX. So splitting factor small. This is have a very big data rate or bit rate on the bit per second. But on the splitting factor 12, we need we get the bitrate on the BPS very small. This is around less than 0.25 bit per second. So this is a comparison with bandwidth. Bandwidth is important parameter, and this is very precious. So bandwidth high, the transmission data is speed is very fast, and the bit rate is high. So the important parameter is use the splitting factor 7 or the splitting factor small, and have the big bandwidth like 100 like 500 kilohertz, and uh, bandwidth, yeah, bandwidth is high and splitting factor is small. So the, the, the conclusion is bitrate can produce high data bit per detik, bit per second. And this is a real-time signal power and chip signals on the ES920LR. This is a spectrogram, and from the spectrogram, so the data around minus 30 dBm. This is a very strong signals on the transmission data. And the right side, this is a chip signal. The chip is consists about the up chip, down chip, and the data. So we can close from the more close from the signals. This is up chip, down chip, and data. This is show the data from transmitting data. And this is a RSSI on the hill and trees obstacle. So from the hills and trees obstacle produce the high RSSI. On the 849 meters, the RSSI is around minus 140 dBm, and this is very big, and obtain the big obstacle, uh, and get the big attenuation. So the signal is very bad on the hills and trees. This is around the 140, but on the distance 710 meters, this is on the line of sight. This is 119 dBm. So we can get the conclusions on hill and trees. This is create the big attenuation on the transmission data, and line of sight more better. This is around 119, almost same on the distance. And the attempt from the 6 attempts, this is around 1 kilometers. ES920LR packet Prasetyo, this is around 93% on the 1 kilometers, and on the 100 meters around 98.9%. So this is still very good packet ratio on the line of sight. And from the different conditions and different obstacles from 4 attempts transmission data on the 1 kilometers, we get the graphs like this. So this is show about the attenuations from the transmitter to receiver with the obstacles, the difference obstacle. 200 and 800, this is so not significant. Why? Because from receiver 1 and receiver 2, this is a different position. receiver 1 and transmitter and receiver 1 on the 200-meter. This is not big obstacles, but on the 700 to 800-meter, this is very big obstacle, and the the distance in the distance is so the increase, but the attenuation is not significant increase. So this is about the distance, but this is about the obstruction on the transmission and the sending on the sending data from the transmitter to receiver. And this is I'm trying to show the four data: air exchanger node, free space, line of sight, and abstraction. So from the abstraction building, this is show the bad signals, and this is around more than 160 dBm on 1 kilometers. And on the free space, looking around the 85 or 83 or 85 dBm. So abstraction building is this is great bad signal, and the free space more better, and line of sight this is around same, around 83 or 85 dBm. And I try to make approximation with this different splitting factor from the experiment. So if the splitting factor increase, the RSSI is more make a weakness. For example, splitting factor 7 on 1 kilometer is around minus 130 dBm, but on the splitting factor 7, this is around I'm sorry, on the splitting factor 12, this is around 140 dBm, but on the splitting factor 7, around 130 dBm. So the difference around 1 minus 10 dBm from different splitting factor. So different splitting factor is increasing the attenuation. And I try to make a simulation on the conditions on the bad weather. So on the normals, this is on the 1 kilometers around 115 dBm, but on the drizzle is not significant attenuation, but on heavy rain, this is so around 100, more than 140 dBm on 1 kilometer. And the conclusions is ES920LR and Neopony board suitable place on the flown by drone with the addition of the splitting factor, RSSI, and position analyzing using the GPS module. And based on the experiment, the RSSI on the ES920LR LoRa experience attenuation based on the type of obstacle that are traversed in the radio propagation process. The line of sight signal has an RSSI of minus 119 dBm at a distance of 710 meters and 10 meters, and a PRR percent of 90%. And the signal drop is also not affected by length alone. Still, obstacles such as in the experiment of sending ES920LR data at the distance of 200 meter to 800 meter have the same relative size. For example, minus 110 dBm to minus 120 dBm. They have recently experienced significant signal attenuation at a distance of more than 800 meters. The splitting factor is affected by distance, The farther the distance experienced by the LoRa ES920LR transmitter and receiver, the weaker is the signals will be. The value of splitting factor determines attenuations and signal power of received signal strength. In heavy range condition, the attenuation signal reaches minus 140 dBm at the distance of 1 kilometer, decreasing around 25 dB. Okay, thank you very much. This is my presentation. Good day and see you.